combination of trying to fix it with the USB stick and welcome to Hadoop call, Hadoop Summit, and thanks Big Data Science for having us here. I think the previous two talks were pretty math, pretty dynamism as well as math. I think this will do a combination of the two. Hopefully, there's still an open question: how much math does it take to fry in the brain? But we're still working on it. Hadoop is a massive opportunity, as some of you have experienced that and have seen it, played with it. That's why you're here. But it's still not the answer for finding solutions to your data science. So there's not enough data scientists, and most analysts do not just Java. Our premise as a company and as a product is to make data science not rocket science, which means that we'll try not to put as much math on our slides, but at the same time, we still want to take and appease some of the mathematicians as well, because they're part of that. How does data science happen today? It's a simple life cycle. There's a bunch of data coming in, both HDFS and 3D. And some of you use rule engines to score those data. People are quite familiar with rule engines. And there is people who try to explore data, people who are trying to model the data, and people who are trying to offline score it. It's a classic life cycle. That's where the modeling, that's where you see classification, regression, the SVM technique you learned about earlier, that's where that gets in. But before you go to the technology of running math, you also have to slice and dice your data sets. Essentially, you want to explore your data, clean it up, right? Deal with messy data, deal with data sets that are not uniform. One column is chopped out in some parts of the data sets. So that's kind of where the exploration phase comes in. Once you model, you have a model, you want to take that model to production, that's your rule engine, so that's your scoring. So that's kind of, so today that's kind of where it's state of the art today. You have a complete different scoring engine, so once you build your model, you store it into PML, and then take it to production sometimes with the ensemble models. PML is massive, so taking it to production has its own interesting challenges. So you run it in database, so some of our tool vendors will provide you ways to run in databases, so you run scoring in database. So that's the other part. But really what you're looking for scoring is a very low latency environment. You want to run 60 micros, it's kind of a common number today you see. You want to run lots of scoring. Now, let's see what a world that looks different. So today, modeling still today is in the megabytes of range. So let's see what happens when you go forward. So, and focusing on just that data science experience, you have exploration, modeling, and scoring. Exploration, as we just spoke about, has a lot of munging. So you have messy data, you do group by, and then modeling is regression, classification, clustering, and optimization. So another common big piece that usually comes up. So that's kind of your big math modeling brick right there. And then you want to take it to scoring. You want to score it in nanoseconds, so you can do hundreds of these models and run them in production. So that's literally, we're taking you from where we are as app developers, J2E people, to Java people, walking you through how day in the life of data science, that's what you do. Now, as H2O is a part of this, bringing tremendous innovation in the central part of this math model. And it's one team that brings all these three together, but our key focus is in modeling, and then bring the ability to spit out code that will go run as scoring engines wherever you want. So that's literally what we do. But we don't want to disrupt the API you have today. You're using R today, SAS, Python. We will work with Excel. Excel is the most, by the way, how many of you have used Excel? Every one of us. Right? Excel is the #1 killer app in this space. If someone tells you otherwise, disbelieve. Because that's actually how people do their modeling today. The Obama campaign was run on an Excel spreadsheet. Right? So we will come to where you are running, not ask you to come to our tools. So we have a JSON API that runs exactly where you are. But if you're in R console or in R studio, it runs from there. Right? If you're in SAS, you're able to call out from there. If you're able to call from Hadoop, Java, you call from there. Excel, of course, is an app that you can plug in and play. So it's the API, where you are. Right? The second part, and I briefly talked about approximate results because we'll get to that. I think knowing an answer very quickly. whether this laptop will survive or boot with knowing infinitely is important, otherwise you want to leave. So the next piece that has been kind of talked about, big data is full of a lot of interesting things. Is more data better? Right? People talk about munging gigabytes of data. Is that actually going to help me get better results, better prediction? And I think there's people on both sides of this coin, and I think the world doesn't have to choose. You get both. Why don't we get more data and better algorithms? So I think the focus of the product is to take better algorithms and then work them at scale, and still get the kind of interactive experience that you're used to at small data. And that's the key. Now, finally, you can't have data science meetup without too much math, so I'll quickly get to the math part. But we believe that a legacy for intellectual is something that we really want to provide to the world. We want to make a math brick that you can take to the world and spread and use in every one of your applications. The way we think of it as math is innovation for the last 10,000 years. It's not today's. We've been using math over the course of generations. And there's no point in trying to patent those math algos and plug them in closed source applications or tools. R has done a tremendous way to actually bring math to the masses. We are fighting a real rich big monopoly, which is 30 years of monopoly in the space, SaaS. And we love the vision of Mahout, and we are here to make that real. We are going to really bring fundamental systems engineering. So we picked up engineers that would have joined Google first 10 employees, style engineers, and asked them to build a really good math platform. So then you can go build great things on top of that platform. Of course, a product's not full without the community. That's why we are here. That's why, and thanks to the Sarkars for having us here. We really want to evangelize this platform as the default platform for writing any math algorithm. There's no other reason to try anything else. And if you're writing in R, of course, we'll make that scale, no problem. But if you're writing in Java or any new server-side language, this is the platform for you. There's one further piece. So we are seeing a lot of different, so it's an open source platform, but people pay us to actually be closed source sometimes. For example, if you're a big bank, if you're risk modeling closed source, so it's a pretty profitable business to actually be able to allow them to build proprietary algorithms. Right? Because the textbook algorithms are basic, but you actually have a very large number of algorithms. Someone in the audience, very smart person, said, there's a torrential rain of algorithms that's going to come. You can implement the first 10, but everyone is going to build their own algorithm. This is the beginning of, just like diversity in human nature, in the world, in the nature itself, there is going to be an algo for everyone's life, and that's kind of what's going to happen as we go forward. So we'll cookie cutter build the first 10, but there's going to be hundreds of these, right? So it's just the beginning of a long journey of building lots of good math algos, and we're going to help build some of those. But one step further, there's applications. People don't actually they don't take tools, they don't consume tools. They use them. They consume apps. So I think the real rich layer above is actually the diverse rich of applications. Whether it's a consumer app that's $10 and promises to make $10 the same day, or an app that's $1 million that 10 people will use. I think there's a whole scheme of apps that we're looking and that we're seeing people actually build as we're working in the marketplace. With that, I want to jump into some math. The first thing that most data scientists do is actually play with linear regression, right? Try linear regression. Just simple, it's the simplest algorithm, so everybody understands. If you try to fit it, you have a single line that cuts your space. Right? The best fit is a very simple linear algorithm. Imagine you have a data set, and this is actually prostate cancer data set. It's a popular log logistic regression algo data set. And by the way, our product is actually free for all cancer research, just a side note. If you try linear regression on this data set, you actually get interesting results. It doesn't actually splice through your data. So that you really are looking for an S-curve, right? So that's kind of your real, you're trying to use the math to help you. And a logic function is a typical, so you actually have two things going on in this GLM. You have a binomial data set, it's a binomial 1 or 0, right? So it's a family of binomial. Then you want to plot, use a logic link function to connect this model with your data. So that's kind of what you're doing here, right? So if you, I mean, obviously I'm going back to basics, and there are some advanced users here in the audience, so forgive me. But really, that slice, that S-curve, is kind of what you're trying to achieve with your model, right? Now, generalized linear modeling is really, how do we scale this? So we took that, we did a simple system. How do we scale this? So Stephen Boyd is a really, really interesting person from Stanford. He's come up with, he picked some really cool algos, invented in the 60s and 70s, brought them to popularity today. One of them is ADMM, right? And I would not hesitate to say it's his now, because he's written treatises on this. On one of the pages, so the core idea of ADMM, I mean, we saw stochastic gradient just a little bit ago. How do you parallelize this function? This is ADMM, just taking a different take on the same. So if you walk with me a little further, I'll double click into how it actually scales. So decompose the problem to something that's local and linear, right? And then try to fit it globally. Right? Kind of the world is very spherical, but you know, when you drive my car, it still looks like a straight road, right? So that's kind of the local linear analogy that ADMM kind of does a global broadcast coordination. Works perfectly well. It's decomposability and convergence, right? So it's really perfectly well for scaling a massive number of machines, right? So, and here's the page number 43 of that large paper. It talks about how do you do lasso, how do you do normalize, and so basically how do you do the regularization and get that high scale. This is the fundamental core of, and that's, of course, ADMM has been generalized. People are actually now asking for more generalized ADMM, where basically if it's a convex function, you can now apply a bunch of proximal operators that will let you to fit any three constraint functions, any n constraint functions, and apply this proximal operator and get the right distribution function. So that's part of it. Of course, we translate that to a H2O implementation, where it's a simple GLM. This is how a GLM would look without any changes. And then we take that to the ADMM solver, which actually decomposes using Cholesky decomposition. So the heart of this is a gram matrix, which is actually kind of one of the limitations that we learned to use. It's a gram matrix, so that is how many parameters. So the smallest, the number of columns or the number of rows, whichever is smallest. Take that by take that, so you have that matrix A transpose. That's kind of the fundamental part where you're fitting one into one node. So that's your, I mean, literally in simple Java, this is public and open, so you can play with that. Now, if the computer permits, I'll try and attempt to get the demo up. Second function, random forest. Someone talked about random forest earlier, SVM classification, so powerful classifier. And of course, we're building more of these. We need a dozen of these by the end of this year, so you can actually use this product more widely. The first few attempts at building this algo took us months. Now it's weeks and in days. So we should be able to give out these functions in a matter of days, and it's open source, Apache V2, so use it. Right? So random forest. Fundamental at the heart of random forest is being able to come up with a very interesting tree that splits and learns one particular feature in an entire data set. Right? Split, understands. Each tree by itself is not interesting. What's interesting is as a key ecosystem of the entire forest, you're able to now understand your data. Right? And so that's one part of it. That's all decision trees. All decision trees are like that. Right? But there's one fundamental part, Bremen, which was fortunate to be the person I met, is that if you randomize at every cycle, so every time you're trying to do a split, just go back to the main run of all the data, you seem to get better results, as opposed to focusing further down and narrowing down your data set size. So that randomization part is kind of the crux of that algorithm. And there are some features that, so how do you deal with NAs? There's some advanced pieces. How do you deal with missing elements? And I think that's the second part. Some of the advantages we bring to the table is we deal with a missing element in a particular column. If it's a missing element, you don't ignore the entire row. So how does this tree look like? So iris dataset and epilepsy. Our key thing is to build a bunch of textbook functions, and then people are using the product to build their own pattern recognition algorithms. And eventually give you a Java API that you can write distributed functions at will, so you don't need to worry about total the time it takes to build complex algorithms. Now, it's easy to install, easy to run, and that's, it runs on this laptop, runs on the cloud, so it's probably time to pull up the cloud. So this was actually a clustered, it's running on 16 node cluster. We ingested all 20 years of airline data sets. Some of you have seen this before, into this particular system. So that's all of the data. It compresses, of course, and it's 12 gigs of data, about 128 million rows. Right? So here's how the row itself is. I mean, you have row, months, kind of. This is all flight takeoff and landing. By the way, it's all takeoff and landing for the last 20 years. So we take this data set and ask them interesting questions on the data. Right? Kind of trying to give you the experience of data science. Of course, people want summary of their data. So let's see how our summary falls apart. So this bunch of, so you want to know which years. There's about 1987 to 2008. You want to know kind of what days were, I mean, every one of the days in the same kind of flights. Actually, we want to see histogram of all flight carriers. Let's see that. So, sorry for the eye chart here. Which airport? That's a good one. There's a bunch of airports here. So you can try to see if there's any particular airport that was more distributed, origin and destination. Now, sorry if I'm too fast here, but carrier. So American Airlines ran 12% of all flights in the US. That's interesting one. Who are the next big ones? US Airways, right? 11%. United 10.8. Kind of makes sense. So sometimes getting just summary of your data is okay. This doesn't fit in any system, right? Any traditional R system doesn't run. We actually chop this off to 2,000 rows to see if it will actually run a summary. So getting summary on your data set is actually useful because it beats sampling. Right? Today you're trying to do sampling, and then you're hoping and praying that that sampling gets you the right result. The second one that you want to do is actually run some algorithm. So what we are trying to do now is actually trying to do a logistic regression, the same function that we talked about earlier, and trying to predict, is my flight going to be delayed, and what are the top features that makes them delayed. If it's cancelled, obviously it's delayed. Right? If you're doing departure delayed, arrival delayed. So let's assume that we don't know much before we fly. We don't know how long it's going to fly. We don't know arrival time and departure time. So let's. And then, of course, this is the crux of the GLM, right? So the reason we want to make this a click-click thing is that we think it's actually it's not actually as dangerous as rocket. It's just not rocket science, and this can be done. In fact, we walk into data science teams and have the person who organized the meeting doing some of this for us. Because then we want to democratize this really and bring it, lower the barrier to entry. Because I think data science is actually not data science. It's still an art piece, and we want to make sure a lot of people get it, and a lot of people can do their part, because find the right algo to fit your data set. That's literally what they're doing. And to answer your question, So this is actually finished 3 iterations of that ADMM we talked about earlier in about 8 seconds. This is all the data we have for airlines, right, for the last 20 years. Right? This is not picking a simple sample or trying to run something on one subset of your data set. This is all of it. It's running on 16 EC2 instances. It's costing about, I would say, $10. $10, yeah, $10 an hour, and that's total. Right? So what is your time worth to you kind of question, right? Literally. Now it's doing a tenfold cross-validation while it is finished its simple model. So here, this is the first model. The model changes once you get the tenfold cross-validation. So you haven't finished experienced data science if you haven't talked about area under curve, right? AUC, that's literally how you're measuring your function's accuracy. And in this particular case, it's saying it's 0.65. It's not that good. It's not that great. Some variable here is not that so good. But it says so that the unique PI is one carrier which was always delayed. It was totally always slow. Atlanta, for example, if you're flying through or starting from Atlanta, you're very likely to be delayed. Or Chicago, right? And Dallas. So and then the first modern carrier US service comes in. Right? So kind of, and then you can also go, so the larger the variable, the more you can, so the more likely, right? So then if you go all the way to the end, the better ones are all the way on the other side. So basically the minus side is pulling you to the better one, right? So you see some of these, it doesn't seem like there's a lot of good ones. There's a few good ones, EA carrier, and someone in one of our meetups discovered that that carrier is no longer in business. So the good ones vanished. So that's, I mean, you actually understood a little piece of your data from your original data set. And this is data science doesn't have to be for the enterprise, of the enterprise, and by the enterprise. So everybody, it's just our data. Literally, big data is our data. It's our data exhaust, right? Quote unquote exhaust. So it's our flights. And some people like us flew, and someone who's flight data. And so there's a ton of opportunity to do data science and improve life. So now I'll add one parameter to see if the AUC improves. That's your crux of data science. If I know my flight arrival has been delayed, can I predict my departure delay? So let's do that. And so, I mean, obviously, there's a ton of good math, the ADMM, and all of this coming together to make this happen in this high-speed fashion. But the crux of it is that data science doesn't necessarily mean that you are inventing math. It doesn't have to be rocket science. Even ordinary people with common sense can work with this, and we want to bring this down to a case where you are interested in solving a problem. If it's cancer, if it's healthcare, if it's in your domain, flying, in your domain of customers, marketing, right, oil and gas. It's your domain. If you're passionate about your domain, you can use these tools and get a lot out of it. So here I have put an airline arrival delay. It's obviously it's very likely that it's going to dominate this overall calculation. Bear with me, and we'll run back into the presentation. But the crux of this thing is that you are capable of doing this, and so you should be able to use it and apply it and solve your problems. We are, I mean, obviously, a lot of other prior art here. We want to make sure that prior art also comes into bearing, and we can borrow heavily from them, likewise, bring back to them. How does this compare, while this is running, how does this compare with other tools? Right? It is hundreds of times faster, and we actually tried to even, I mean, we kicked off some of these results on our on Mahout and on SAS, and some of them are still running. SAS, of course, finished, but there's no way to run 16-node SAS without paying a really ton of money, and so that's literally so. I think of AUC 0.83. So it's much better predictability now that you actually added a net new variable, right? So the other thing that customers usually do, actually they try to take this data and cut it down to pieces, right? So you can slice it down. So we actually have a console here where you can take the first million rows and So you chop the data set into different pieces, training, testing. So this is a small console which speaks like R, and eventually this will come from R so that you don't have to worry about learning a net new language. And obviously it's running. So this is running distributed from all the machines, going and finding the right chops. Why is this fast, right? So the curse of the last reducer, I don't know how many of you have heard of the curse of the last reducer. The curse of the last reducer is that MapReduce, I mean, there's a slide that I'm sure in there, it says, wait mom, MapReduce is not fast. Why? MapReduce is parallelism, but you have the parallel pieces, the reducers are postponed. Nobody talks about sort and shuffle, right? Big giant part where you actually spend time. So you have the curse of the last reducer. Your last reducer is the time it takes to do the entire computation. So what we have is fork join, which is a very fine-grained parallelism, which we think is the future of all parallelism, is that you actually can reduce as things are happening, so that you actually get an approximate result at each stage, as well as you can then avoid this giant reduce step that needs to happen to get your computation out. And so that's why so the second piece, of course, we are memory, in-memory, and traditional technologies are IO-bound. So those are the two big reasons why this thing is fast, right? Memory and fork join, which is a lightweight parallelism and really, really fine-grained. So you actually get parallelism at every step. So that's, literally the piece. And so the munging experience, which is where we were looking at, you want to slice your data, you can apply filters, so you can chop that data across multiple machines and run filters on it, transform those data sets, whether you want a log transformation, because you have a Python distribution. So that's the other pieces that we have added to the, upon request from customers. People wanted to do Groupwise, we had Groupwise, right? So that's kind of other pieces. But really, every piece that you've experienced, including this piece, is a JSON query. So you actually can, so if you go back to the model, so that 1 million rows that we chopped up, you can run random forest now and see what it does. So kind of try to use it all. So with random forest, you don't need to figure out what's missing, what's not, and try to run the entire, all of it, and try and see what random forest does. This is actually the yes, no, so it's much easier classification problem for random forest. And of course, it's really good. It overfits small data. So there are different technologies, different math techniques, and this is a very popular technique for black box understanding and learning your data set. And this is it. Again, all of this is completely a JavaScript scriptable, so everything here is a JSON. So you actually can program this into your both JavaScript APIs, Python APIs, R APIs, right? So and we have the base stuff created so you can actually connect them without having to invent the core. So that's the kind of completes what I wanted to talk about. I'm pretty sure there's some performance numbers we created. So if you have questions, it's really a good time to go after them. How do people use us? We have a bunch of fraud detection use cases, a bunch of customer behavior, market analytics, that's really popular. People try to figure out whether a particular lead will convert or not. So, questions? Yes. So there's a Java API, there's a JSON API, and that
literally like a REST API.
There's a REST API, of course. So the JSON is kind of the REST we have. So .html was what we were presenting, what we thought was worth presenting for using Bootstrap, which is a popular Twitter Bootstrap CSS. But literally, if you delete this HTML, that's how people use it, right? The other piece that we have is, we built a barrage of test suites. All our test suites are essentially Python packages, right? So we're doing GLM tests, the buzzword in some sense. In some ways, actually, so Stanford, Purdue, SUNY, we've percolated a lot of universities where people are actually running semester programs on this software so that they can actually start playing with the software and adding missing pieces. So, so there are two layers. One is the program that's not Java.